Okay, everybody, welcome back. I hope you had a great long weekend. Today is Wednesday. We are covering the chain rule day 2. Hopefully you are actively working on the steel drum and pipeline projects. Let me know if you have questions on those. We've got some quizzes coming up. Both of them are take-home quizzes. We'll talk about them as we get closer. Any questions on the calendar? Okay, so one thing before we jump in on page 12, I had said that on the syllabus you have a choice between 2 grading options for me at the end of the semester, but you need to make that choice today. So hopefully you've thought about it and you've chosen one of these 2. I suspect almost everybody in here is going to choose the homework counts for 5%. The alternative is that homework counts for 0%. And that extra 5% gets added to your test grades, okay? So most of you, I think, are gonna go the homework counts way. During the activities today, I will ask you which way you are going. All right, so let's jump in on page 12. Today we expand our ability to use the chain rule to differentiate functions defined numerically and compositions of more than 2 functions. We also learn that dogs do calculus. That is a teaser for the activity. All right, let's jump into number 1. Sometimes we have to apply the chain rule repeatedly in the process of evaluating the derivative of the stuff. We might have to use the chain rule again. So for example, here in number 2, it says find the derivative of the following. Y equals e to the sine of the quantity 2x minus 4 all cubed. So let's try this one. So we have to identify, there's a lot of functions buried inside of other functions. We need to figure out what the overarching outer function is because that's the one that dictates the beginning of the process. So is this entire function some stuff to a power? No, the stuff to a power is buried inside. So don't look closely there. Is this entire function sine of some stuff? No, that's up in an exponent. Is this entire function e to some stuff? Yes, it is. So this is an e to the stuff rule. We don't officially have it, but I did show you last class, or I told you last class, that the derivative of e to the x, surprisingly, is just e to the x. It is itself. We will see that officially soon enough. So then we will use that rule first and foremost. dy dx equals, so the rule for e to the x is just e to the x. So the rule for e to the sine of all this is e to the sine of all that. Right, e to the x stays e to the x, so e to the sine of all that stays e to the sine of all that. And if there weren't a chain rule, we would be done, but the chain rule says now you have to multiply by the derivative of the stuff, the derivative of the thing playing the role of x. And the thing playing the role of x in our problem is all of that. So we need to next multiply by the derivative of everything I just circled in blue. And now we play the same game. Is everything I circled in blue a bunch of things to the third power or sine of a bunch of things? It is sine of a bunch of things, right? The third power is still buried inside. We aren't there yet. So the rule for sine of x, again, we don't have it formally yet, but I gave it to you last class. The derivative of sine of x turns out to be cosine of x. And so the derivative of sine of all that stuff is just cosine of that same exact stuff. Right? Sine of the stuff becomes cosine of the stuff. That's our derivative rule. And again, if there were no chain rule, we'd be done. But we need to multiply by the derivative of whatever is taking the role of x. And so in my circled blue thing, what is taking the role of x? It's 2x minus 4 cubed. All of that needs to have its derivative multiplied out here.
So when x is like f of x, the derivative of sine f of x, cosine f of x times.
It is. That's right. It's not just times 6, but I think there's a 6 that's going to be in our final answer. So I see some stuff to the third power. So this is a power rule. If it were x to the third, it would be 3x squared. So it's like that. But instead of 3x squared, it's 3 what squared? 3 2x minus 4s, right? Then one last piece is that if it's not just x cubed, but it's something more complicated than that. Let's say I'm running out of space in here. Oh no, blue, black, about this guy. We need to multiply by the derivative of the thing playing the role of x. It's not just x cubed, it's 2x minus 4 cubed. And so we need to multiply out here by the derivative of what's circled in black. What is it? 2. Done. All right, and so Hunter said, hey, is it 6? Yeah, it's 6. I mean, you can multiply the 2 and the 3 together now. All right, questions on that?
This is adequate, writing it like that. That's okay.
Yeah, that's good. Okay. The only simplification you could even do is the 6. Maybe pull the 6 in the front. That's it. Yeah, you can't bring the 6 into the squared. Yeah.
So instead of working from the inside out.
Outside in to dictate, yeah, because you got to figure out like what is the first rule to apply. Like it's really tempting to say, oh, I see a 2x minus 4, so I'm going to multiply by 2. But what do you? I mean, there's nothing here that says multiply by the derivative of 2x minus 4 until you're way inside of there. So you got to look outside and then gradually working your way inside. And last class we saw things that were like, you know, like some complicated thing with x divided by some complicated thing with x versus some complicated fraction to the third power. You know, like maybe there's third powers on these guys, but like this is not, the first one is not a quotient rule, not first. Right? The first one is some stuff to the third power, and when you do the derivative of that stuff, that's a quotient rule. But the other one is a quotient rule first, and then at some point we might have more things to do on top and bottom when the quotient rule tells us to take those derivatives. Okay, number 3, given the table below, all right, so that's multiple applications of the chain rule. Here is a numerical example of the chain rule. Given the table below, find the indicated derivative at x equals 1 if possible. So we are looking for the derivative of this thing right here, the crazy function f of x, that whole thing cubed, minus 5 times g of x cubed plus x squared. So we want the derivative of that thing evaluated at x equals 1. Sadly, we can't apply like any of our basic derivative rules. There's no like sine of x, there's no e to the x, there's none of that stuff. It's just information in a table. And somehow some of those numbers are going to be relevant to us. Let's see. Okay, this thing equals. All right, first of all, looking at this entire function as one unit, I see a big subtraction sign in the middle. That makes me really happy because derivatives around subtraction behave nicely. So I'm going to copy that big subtraction sign in the middle. And I know that I am justified to just do my 2 derivatives separately and subtract them at the end of the day. All right, let's start with this f of x cubed. Temporarily, forget about the fact that it's called f of x. If I just had something cubed, the derivative would be a 3 times that thing squared times the derivative of that thing that I'm covering up, right? That's our brand new chain rule. We actually saw this exactly up above. 3 comes down, copy the stuff, subtract 1 times the derivative of the stuff. Well, that's exactly what we're doing here. We just have to make sure we use the right symbols. 3 comes down. What's the stuff? F of x. New power is 2. But then times the derivative of that thing that I covered is symbolically f prime of x, right? We can't do anything. Like we're used to like physically writing derivatives using our fancy rules, but here it's just symbols. Okay, and then minus. Okay, 5 times. I like 5 times because I know that in my derivative it's going to be 5 times, right? It's a constant multiple, so it gets copied. Okay, g of x cubed plus x squared. This is the trickier one of these two, I think. I'm going to get rid of it for a second. If this said just g of x, what would you write symbolically for the derivative? You just write g prime of x, right? Okay, so I'm going to write that. Don't write this because it's not quite right. But if it was just g of x, we would just put g prime of x. Okay, but it wasn't g of x. It was g of some complicated things. And so you know how we always, like when we do our basic derivative rule, we always copy the stuff one time, right? You copy the stuff. This right here is the stuff. That right there is the thing that we have to copy. And so it's not g prime of x, it's g prime of the stuff. We'll revisit that in just a second. Times the derivative of the stuff. What is the derivative of what I underlined over there? 3x squared plus 2x. So I think that the trickiest part for most students is this g prime of x cubed plus x squared. Like the times the 3x squared plus 2x, that's pretty straightforward. Just multiply by the derivative of this stuff. So what is that g prime of x cubed plus x squared? Well, let's come back up to this concrete example up here. And suppose that this was just y equals e to the x. What would the derivative be? It's just e to the x, right? But it wasn't e to the x. It was e to some, like sine of blah, 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 right? And so what was the derivative? It was e to the sine of blah, blah, blah. And then the chain rule says, like multiply by another derivative over here. So like if you have like the derivative for e to the x, you have a rule for that. You apply that rule, but you don't put x in there. You put the stuff that was originally up there, right? Well, symbolically, I have a way to write the derivative of g of x. It is g prime of x. But in this case, it's not x, it's x cubed plus x squared. So I have to put that thing right into my function, into my g prime function. I know that I don't have a real strong way to sort of convey that idea. I wish I had something better to explain what's going on there. Do a couple of examples and you'll start to see the pattern. But that right there is just, it's exactly the same phenomenon that we saw more concretely up above. Okay, this right here is the derivative rule for any x. This one says, hey, x equals 1 is what we care about, so we're just going to plug in x equals 1 everywhere. So at x equals 1. And so I'm just going to copy that entire thing. 3 times f of 1 squared times f prime of 1 minus 5 times g prime of, and then just really being naive here, copying 1s everywhere we see x's. Okay, I'm not quite ready to use my table real soon though. 3 times f of 1 squared, that's easy enough. Times f prime of 1, that's easy enough. Minus 5 times, but let's get our hands on what's really the single number in the parentheses. That's 1 cubed plus 1 squared, that's just 2, right? Times, let's figure out what's in this parentheses. Is that 5? So to finish this problem, now we finally get to use the information in the table. In the table, do you find f of 1 somewhere? Great, so we're going to replace. Do you see f prime of 1 somewhere? Yeah. Do we see g prime of 2? Yeah, it wasn't obvious to me. Like, all right, I understand why this table has an x equals 1 row. I have no idea why the x equals 2 row was there. Well, now I see. I needed g prime of 2. That's the only thing I need from that row. Okay, equals 3 times. What was f of 1? Is 1, and that's getting squared. Times, what was f prime of 1? 3. Minus 5, what was g prime of 2? 7. And then times the 5 at the end. No, 175. I think I've got that right. All right, so again, I know the tricky part was that g prime of x cubed plus x squared. Questions on this one? And I'll own up to when I was a student taking this AP Calculus class, like I was really good at the example with the e to the sine and all that. I could do like repeated applications of the chain rule all day when you gave me functions, like particular functions like e and sine and x to the third. But what I was not in a position to handle was stuff like this. I could not have done this problem when I was taking the AP Calculus class. I didn't understand the chain rule well enough. I could do it only if I had like specific formulas given to me, but I couldn't do this numerical thing. So yes, it is harder than the specific formulas, but it's something we want to push you to understand. Like it is a deeper understanding of the chain rule that's required to answer questions like this. Okay, number 4, 3 versions of the chain rule that all say the same thing. So in one, to take the derivative of a composition, you take the derivative of the outside function, evaluate it at the inside function, then multiply by the derivative of the inside function. Ryan had said, hey, so instead of working inside out, we're actually working outside in. Yes, that's exactly what that says. Start with the outside function. Okay, number 2, the mixed notation version, f of g of x, that's composition. And so it's f prime of g of x times g prime of x, or in a little bit more common language, f of the stuff becomes f prime of the stuff times the derivative of the stuff. And finally, Leibniz notation, which we haven't seen, but you will see in an activity today, dy dx. We know that's the derivative of y with respect to x. But if there's like this other function z kind of floating around someplace in between, dyzd times dzdx will be a way to get the final derivative. That dzdx is supposed to represent the derivative of the stuff. That'll become more clear during the activity. But even if it's not clear right now, if you just look at these guys like fractions, like if they were just numbers, and you cancel the dz's, what do you get? dy dx, which is exactly what, I mean, so like even if we don't understand how to calculate using that formula, at least it looks reasonable, right? Like just it's a fraction equation. Okay, so 2 activities here. One of them is examples of the things that we just did, and then the other one is about a dog named Elvis. So let's see how far we can get through those 2.